Hello, welcome to the recording of a panel event discussion on full shape versus templates in the context of analyzing galaxy clustering data. If those words don't really mean anything to you, then just wait, I'll define what it is in a bit. This was a panel event run by Cosmology from Home organizers this week, partially as an experiment for Cosmology from Home, but also as an interesting event in its own right. Only I'm visible in the recording, but it was definitely a full team job, especially in preparing and thinking about how to run the event. I should also especially mention Mariana Vargas Magana, who, although not appearing on camera, was the co-moderator of the event with me. The discussion is between Hector Gil Marín, Marco Simonovic, and Simonovic Tröster, who introduced themselves more thoroughly in the video itself. The panel event was a little experimental in that the panelists discussed the topic in advance via email. Our hope was that this meant that they were more prepared to respond to each other's perspectives during the event itself. Normally, you just get to respond with your first instinctive thoughts in response to other people's instinctive thoughts. But this way people could respond more thoughtfully and even respond thoughtfully to other people's thoughtful responses. We also tried hard to frame the event to the panelists and audience as a collaborative pursuit of understanding rather than an adversarial debate. I introduced the topic more thoroughly in the video. Unfortunately, my video is very blurry at the beginning, but the audio is clear and the panelists' videos are all clear. I hope you enjoy the video. As far as the topic, I'll just give a super quick intro to what the issue is that the three panelists will be discussing, and then they'll introduce themselves, and then we'll get started. To start very, very broad, we are measuring billions and billions of galaxies, and somewhere inside that collection of, I guess, four-dimensional information or three-dimensional information, where they are and what redshift they were measured in, there's cosmological info. But how do you compress that data to find the cosmological stuff? So for today's discussion, we will focus mostly on the power spectrum, although in principle, there's information beyond that, and that extra information coming from nonlinearities might come up in the discussion, but in principle, we're just focusing on the power spectrum. But even in the power spectrum, there's a lot of info. There's the full Z dependence, there's the full wave vector magnitude dependence, and then angular dependence because of redshift space distortions. And that is a lot of information. So there's a few ways that one can choose to study that. You can do the full shape. So you have your model and you can predict the full generality of this power spectrum and then do a Monte Carlo Markov chain to find parameter constraints. Or instead you can choose certain templates that compress that information even further, that try to capture the results of certain independent physical effects. So a few examples of that might be just finding where the BAO peak is, where the baryonic acoustic oscillation peak is, as a function of line of sight and angular distances. And that then is coding the effects coming from the sound waves in the hydrogen of the primordial universe, but little else. So you're really focusing on that one physical effect. And there are different motivations for doing full shape versus doing different templates. And the general pros of the full shape are that you get tighter constraints, but cons are that it's slow and that it explicitly depends on a model, whereas templates can be faster and more model independent, but they don't use all the available info. And it can be potentially tricky to extract information about a model from a certain template. So the panelists all agree that both of the methods have their place to answer certain questions and that they require care to implement, but where there might be disagreement is on what specific questions each is answering, how important those questions are, and then precisely what care needs to be taken. So that's the intro to the broad topic. Let's go in alphabetical order by first name. So Hector, then Marco, then Tillman. Just quickly introduce yourselves.
Right, so I'm Hector Gil Marín. I'm a postdoctoral fellow at the University of Barcelona. And in the past, I've been working within BOSS and eBOSS project. I have led the BEO and RSD analysis in this project using the 2-point function, but also the 3-point function. And right now I'm involved within the thesis spectroscopic survey, and as well I'm a convener for the BEO and RSD analysis within this. And I've also the author that has proposed one strategy for blinding the data precisely based on blinding the BEO and RSD signal in future DESI data.
And so, hello, I'm Marco Simonovic. I'm currently a staff in the theoretical physics department at CERN. And related to large-scale structure, my expertise is in perturbative modeling of the nonlinear density field. And also recently, I've been involved in a couple of analyses that used full shape to measure the cosmological parameters.
I'm Simonovic Tröster. I'm a postdoc in Edinburgh, coming more from a weak lensing background, but I've been doing joint analyses between weak lensing and large-scale structure probes, trying to find ways to combine them in a consistent way.
Awesome. Thanks, everyone. So there's probably 3 separate directions we're looking to take the discussion today. I'll just give a quick signpost of what those 3 are. So one of them is a very kind of general discussion about what we actually want from a cosmological analysis. Is it parameter fits or model comparison or testing how well a model describes the data? The next one will be how model independent templates actually are, and maybe more precisely how model independent can they be, and how to use them in as model independent a way as possible. And then the third general direction will be when you've got different data sets and they're not independent, how do we combine those separate data? And is it more difficult for templates compared to the full shape? And if it is more difficult, how does one overcome those difficulties? What work needs to be done to reach that point? So let's maybe start with what do we actually want from a cosmological analysis? And I'll start with Hector. You had some interesting thoughts about what you think one wants and what one might not want. And hopefully Marco and Tillman will be provoked by some of the things you say into wanting to respond.
Right. So, I mean, to be very quick and straight, I think we all have this standard model of cosmology, which is lambda CDM. But we know that this model cannot be the ultimate model. And we know this model is just an effective model, but we know it doesn't make any sense to be like a fundamental model. So at some point it has to break down. And I think that's one of the key goals of the future spectroscopic survey, at least from my point of view, is to break lambda CDM, to find something that it doesn't make sense within lambda CDM model, and then therefore we can understand something further. If this is our goal, is to break lambda CDM, I think that assuming lambda CDM when fitting the data, it's not a good strategy.
Okay, but so when we're doing a cosmological analysis, one of the things you were saying, if I remember, was that you thought testing whether a model is correct is more important than doing a parameter fit.
Right. I mean, the thing is, when you assume a lambda CDM, you're just fitting the parameters of this model. And if this model is not correct, then it will create some internal tensions, but you will get, in any case, some best fit parameters. But then what you learn from this in terms of whether lambda CDM model is the correct model or not, I don't think you are going to learn much. What you will learn is to use some effective, so if you fit BEO, you fit RSD, you fit the transfer function independently, then you check whether this makes sense within a certain lambda CDM model without any internal prior you put when you fit those. I think you have much more power to learn things. So such a way that within lambda CDM, the BEO predicts this parameter to be whatever, but the transfer function you measured as well from power spectrum predicts this parameter to be whatever. So these two parameters are in tension. Therefore, you know that there is some inconsistency within lambda CDM.
Cool, thanks. Marco or Tillman, do you want to maybe defend the concept of just having your model doing parameter fits to the model, which is, I guess, more what's happening from a full shape analysis?
Well, yes, but yeah, I think that sometimes this is raised as one of the objections to the full shape analysis, that you always have to assume some cosmological model and then compare the predictions of this cosmological model to the data. I don't think that this is a problem. In fact, I think that this is the strength of this approach, because even if you wanted, I guess what Hector wanted to say, maybe another strategy is to measure some more model independent, and we can discuss later to what extent things can be model independent, but some more model independent numbers. And then in any case, even if you do this, you still have to interpret them later on in the context of particular models, right? You always want to boil down the questions about our universe to the questions about some particular model. For instance, if you measure F sigma 8, this maybe you can do in a model independent way somehow, but this only tells you characterizes the late universe nonlinear field, tells you something about your data, which is very good. But you always want to ask, what does it tell me for something else? And usually the questions that you want to ask are, what is the composition of our universe? What are these different, what are the different species maybe? Like, how do they interact and evolve throughout the cosmic history? What are the initial conditions? So all these questions always make sense, and they can be phrased properly within some cosmological model. And this is why I think that at the end of the day, no matter how we do analysis, we always want to compare the data eventually to some cosmological model. And so the full shape does it in one step rather than going through some compressed quantities. So since this is our final goal anyhow, in my view, I don't think that it's a problem to do it in one go.
Yeah, I think fundamentally what we want to do is we have a model that describes the universe, or we have multiple models, and there are statistical ways to decide which of these models best fit the data. And once we have found a model that we are convinced that it's physically sound and that fits the data well, then we are done. I don't think we can do anything more than that with the data we have. And whether that model now is a full shape model or some template-based thing, from a statistical point of view, I don't think it makes a difference as long as it describes the data in a consistent way.
Well, I think it does a difference because it allows you to test internal tensions that this model can have. And not only to test them, like you can say, well, I mean, if there is internal tensions, it will return me a bad chi-square. But then bad chi-square doesn't tell you anything. It just tells you that there is something wrong, but you don't know whether there is something wrong with the data or there is something wrong with the model. It could be some systematics in the data that you haven't corrected properly and then give you a bad chi-square. Doesn't mean lambda CDM is wrong. But if you do this with these physical variables and you want to check whether this is a smoking gun for lambda CDM not to be correct, then you can check, you can perform internal consistency checks. And this is something that you cannot do with the full model because you go further, you go straight from P of K mu to parameters. So it's like a black box. You don't know where the information constraining this specific parameter comes from. You don't know whether the constraints on omega matter, for instance, comes from BO or which part comes from BO, which part comes from RSD. You don't know anything. It's just a black box. It goes straight. And I think you are losing control on this intermediate step, which are very important when you want to actually test whether this model makes sense or not. Another thing is like if you are fitting a simulation, you know, the simulation is lambda CDM for sure, then this is like prior you can put, it's true, and you go and fit your parameters, that's fine, but that's not real life.
Michael or Tillman, do you have any response to that idea?
Well, perhaps I can say that one important thing that Hector brought up now is that there is a possibility that perhaps, for instance, you have some systematics in the data, and then what do you do? I think that for the discussion of full shape versus templates, maybe it is better not to imagine this. And this may happen, but I think that it will plague also the fixed template analysis. Imagine that, for example, your data is somehow biased completely. You will be in trouble either way. You will have bad chi-square and you will not know what to do with it. So this is one point. On the other hand, I have to say that I do agree to some extent with this logic that perhaps if you want to be very cautious, the first thing that you want to do maybe is somehow to look at your data in a way that where you really maybe understand or look at the properties of your density field, such as F-sim8 or the BEO scale, which you do understand intuitively, and maybe you can devise some ways to measure it like in a more robust, more independent way than the others in order to get some feeling that everything is okay. But in any case, again, ultimately, if you think that everything is okay and that there are no some systematics or something like this, you have to convert these numbers into some parameters for a cosmological model either way. So this step of doing, in a sense, a full shape analysis, rather than fitting the full P of K, you fit a few numbers, but this step is always there and it has to be done at the end. So under assumption there is no systematics, I think that they should be equivalent.
Yeah. Just before any reply to that, does someone want to just unpack F sigma 8? I don't know exactly what audience we have today, but you guys have been saying it a few times. Do you just want to say what it is and why it's interesting, how it's measured? Just a super general overview of the parameter.
So can I give like a very quick introduction, and then this actually will tie to the thing I wanted
Awesome.
to say.
Yep.
So in the compressed model, you basically in the fixed template, you compress your PFK data into some sort of variables. Typically, it's alpha parallel, which is the BO along the line of sight, alpha perpendicular, which is the BO across the line of sight, and F times sigma 8, where F is the growth of a structure, the logarithmic growth of a structure, and sigma 8 is the amplitude of fluctuations of your power spectrum smoothed with a top hat filter of 8 megaparsecs over H. Right, so these three classical variables in terms of compression are actually very different physics. So the BO essentially gives you information of the late-time universe and also contains information on the absolute size of the ruler at CMB times. But late-time universe only allows you to constrain like a combination of these two. So essentially within lambda CDM, this is interpreted as H times RD in one direction, and dA is just the integrated of the Hubble function from 0 to the redshift you see. These are like typically background expansion history variables. On the other hand, you have F sigma 8, which is a variable which is perturbative. So it's the physics behind this variable is very different from the others because it's like perturbative physics. It's sensitive to GI, it's sensitive to the velocities, the peculiar velocities of the galaxies, whereas the other is a Hubble flow. So following this quick introduction on what typically large-scale structure measure, doing the compressed variable way allows you to disentangle this sort of physics. So imagine you want to do your analysis and say, I want to infer variables only using background expansion, or now using background expansion combined with this other thing, or any combination of this. The compressing the variables allows you this sort of game playing, like let's play this game of I'm not going to use this parameter now, I'm going to use this other two, let's check whether this makes sense, etc., etc. So this allows you a lot of internal checks within your model that you are completely not doing if you do the full shape analysis, because you essentially put everything together and ask them, give me the best constraint you can, but I don't care where this information is coming from.
Can I maybe try and direct the conversation in a good way? So I mean, try and direct it in a good way. So Marco and Tillman, I get the vibe that maybe you don't actually disagree with Hector about that being a totally valid use of templates. So maybe just nod if you agree that is a good use to check internal consistencies and whether these specific things. So then maybe the discussion we could proceed with is, I think Hector might still have a little bit of reservation about whether just a parameter fit to lambda CDM or even beyond lambda CDM with a varying equation of state or with neutrino masses or with whatever, that just fitting parameters is a useful thing. Is that a fair summary, Hector, that you're not entirely sure whether it's useful? And if it is a fair summary, do Marco or Tillman want to defend parameter fits? So first of all, Hector, just nod if it's a reasonably fair summary.
No, I mean, definitely you can learn things, but I don't think this is the only thing you have to do.
Okay. So let's maybe just quickly talk about the things that you can learn anyway, and then we can potentially move on to model independence after that. But yeah, Marco or Tillman, do you want to talk about what the benefit of just a full parameter fit is?
Well, perhaps, I mean, I don't know, I can say maybe a few words. I think that the usual way the standard way to maybe defend it is just to say that, first of all, this is the basic, like the most simple and textbook example of how do we do analysis. So we have some model, we make theoretical predictions, we run MCMC compared to the data, given some covariance, and we see what are the best possible constraints in the cosmological model. This is good because it is guaranteed to give us unbiased results, assuming no systematic errors in the interior observation, which is a separate problem. And I think it's a relevant problem, but maybe let's not discuss this at this stage. And not only that it is unbiased always, but given some cosmological model, it is guaranteed to give optimal error bars on cosmological parameters for this cosmological model. I think that this is maybe what you were referring to at the beginning when you said that the full shape somehow has more information. I don't know if this is the proper way to phrase it. It's just that if you fix some cosmological model and you measure cosmological parameters this way, you will get everything that you can from the power spectrum. And finally, one other important, I think, point is that this can be always done for any data set and any theoretical model. So for instance, the benefit of this is that you don't have to rely very much on the CMB, for instance. Or maybe you want to really analyze your large-scale structured data, or even different chunks of your large-scale structured data separately, let's say before you combine them and things like this. So these are, I think, briefly some important advantages of the full shape analysis.
No, just saying I completely agree. And then just saying if you would want to go just beyond like a clustering analysis and put in something like galaxy lensing that depends on the same bias model because you use the same galaxies, then you anyways need some bias model. And for full shape analysis, you already have that part, whereas it's a template analysis, you would have to replicate these parts. Well, there are caveats because reclancing is a mess in that regard anyways.
Cool. I think the next topic will be on how model independent templates are or are not. But can I just maybe re-ask the question? So I thought that Hector had a point, but I thought was a reasonably compelling one of, let's say we already know that a certain parameter within the lambda CDM model, maybe omega matter is, I can't remember whether it's 0.3 something or 0.2 something. It's 0.3 something, right? And then let's say we know it was 0.32 and now we measure it to be 0.321 and then we measure it to be 0.3212. Like, what are we gaining? What information are we learning by getting this extra precision on our model parameters?
Well, I think that we do gain something. Let me maybe try. I think Hector said that in this full shape analysis, of course, you're imposing some model from the beginning. The method will give you some posterior, no matter what. And this is, of course, true. You will find some island where your parameters converge. And then you may ask yourself, so what do I do with this then? Whatever data you fit, the lambda CDM fit will always produce some constraints, okay? I think that the chi-square then or the quality of this fit, and maybe not even the chi-square itself for a given model, but in particular, if you want to test some other hypothesis, so you have another model, let's say, for which you think that may be a better fit to the data, then there are ways to tell which one of the two is a more likely fit to the data, or which one of the two is more likely to be the correct model of the universe given our observations. So, but even if you have a single model, let's say lambda CDM, and you keep like measuring cosmological parameters to higher and higher precision, at some point, even in the full shape analysis, something will break down. You will see that your model doesn't feed the data very well enough anymore. Your chi-square will be terrible. And then you will know that something breaks down. And I do agree with Hector that maybe just looking at the fit, you may not be able to tell what exactly breaks down. And then you can look at the residual plot. You can start seeing like if you have some features in the residual plot, which you can maybe guess where do they come from, etc., etc. So I think that there is a value in like using even a single model. But if you want, maybe more interestingly, the full shape allows you to explore different models and then compare them with each other. And you're, as I said, importantly guaranteed to always get optimal error bars for each model that you're considering. And this has led to some interesting results recently, for example, for the models that cover dark energy, superlight, ultralight axions, etc. So I think this is the benefit of it.
Cool. And unless you feel you have something super important to respond to that, Hector, we can move on to model independence. But if you do, like in a few sentences, that's fine. But then I won't let Marco or Tillman respond to that.
The thing is, I mean, if you assume a bad model, then you will get biased parameters, and I'm not sure you will. You say that you will get bad chi-square, but sometimes this difference in chi-square might be so small that you are not really able to identify and discriminate among models, and these models may predict you different internal parameters. So I don't know. I mean, again, I mean, there are a lot of subtleties in these things, and when you do compressed variables, you know that there are some variables which are more robust than others. And you lose this gain with the direct fit.
Okay, if we want to continue that discussion later, either the panelists themselves know each other and can contact each other, or we can have it in the Slack. But let's move on to model independence, because I think this is somewhere where there'll be something quite productive. So the maybe initial potentially naive, potentially not naive claim is that templates are more model independent than a full shape analysis, that you're somehow, I mean, everything that we do in cosmology is in some sense model dependent. We're not just magically interpreting the universe without a model. We use general relativity as our model of gravity, unless we're testing beyond general relativity. We have chemistry as our property of how stars emit light. So everything is somewhat model dependent, but the claim is that templates can be more model independent, that you're modeling some particular process in the universe, not the full lambda CDM in all of its generality. So maybe Hector give a better version of the templates being model independent than I gave.
I think they just have more freedom to fit like different shapes for the power spectrum. Like, I mean, the more obvious is that lambda CDM put constraints on the relation between BO along and across the line of sight. Whereas the template fit, you treat these two as independent variables. So there is a clear model prior between these two that fixed the pairing template or the full modeling puts you, and not only between BEO, also between BEO and transfer function. So it puts constraints between late time physics phenomena and early time physics phenomena. And actually these are important not to put these constraints, because you actually want to check whether late time phenomena agrees what we predict with the early time phenomena. So I think this is one of the key points of the whole thing.
Cool. Okay, so Marco, do you have anything in particular you want to respond to that?
Right. So, well, I think that I'm not entirely sure. Maybe I think that a good figure to show is the figure from the latest Hector's paper, the one which shows the fit. So I think that from this figure it will be somewhat, I think, clear what would be my general concern. And then we can discuss in detail like how big is this concern in practice, and what are the possible problems. This is a figure from the latest Hector's paper, and what is shown here very briefly, like the gray lines, I guess, are the contours that you get using the template analysis only for alphas. Then the yellow lines also include F sigma 8. And then the blue contours are what you get if you feed the same data, assuming some cosmological models, lambda CDM, and do the full shape analysis. So then Hector chooses, like, obviously the cosmology which is wrong, which is this red star. So it is not like sitting within the 2 sigma confidence level of the full shape analysis. However, it is compatible with the results of the fixed template analysis. And then we can take a look at the next slide. And so now he's testing whether choosing so different cosmology really leads like to some biases in measuring F sigma 8 and then various distances. Okay, this is shown on the left-hand side, the panel on the left, where you can see that, roughly speaking, both full shape and this cosmology which is far away from the truth in the units of full shape error bars seem to produce similar error bars on these compressed parameters. However, if you look on the right-hand side, you will see that the red curve obviously doesn't fit the green data points. And compared to blue, this is obviously much worse fit. So now, this is an example, I think, that Hector would argue, and Hector, please correct me if I'm wrong, that this shows that even choosing the template which is far away from the truth still measures F sigma 8 and these distances in a reasonably good way. It will not bias your estimates. So in that sense, it's very robust, you would say. On the other hand, my worry is always that if you fit these data points, because in order to find these rescaling parameters, you have to feed these data points with a template which is so far away from the truth, it is clear that you may, first of all, you will have terrible chi-square, which I don't think you will not know what to do with, because you will not be able to tell whether this is some systematics in the data, your template is really far away. And the second thing is that even if you ignore chi-square, because you're fitting the wrong template to the data, the fit may adjust in a way which will bias your parameters. I mean, this is not unimaginable to happen. And this is, I think, a general concern. Whatever fixed template analysis you do, I think because you're choosing some template which you don't really know if it really corresponds to the truth before you do the full shape analysis or combine with Planck or something like that, then there is always a problem, a potential problem that you may get biased in estimating. Now, with these error bars here, there seems not to be, the bias is not there, but the real concern, of course, is what happens in the future where we have much more precise data. And in a nutshell, this is my concern with this method. This is why I believe that there is a small cosmology dependence, residual cosmology dependence, which can cause a lot of problem in the future.
I think here we are mixing a few concepts, and I mean, maybe I can explain the right way to read this paper. Could you go back to the previous slide again? So this is like how the standard classical approach has performed. You compress all your power spectrum information in 3 variables, which are alpha para, alpha perpendicular, and F sigma 8. And these are the contours shown in gray or in orange if you use post-reconstruction. But
sorry, Hector, maybe just quickly again unpack alpha parallel and alpha sigma in just one sentence, in case people haven't heard those terms before.
So what standard classical analysis measures is BO along and across the line of sight and the amplitude of perturbations. So these are compressed in 3 variables, which are alpha parallel, alpha perpendicular, and F sigma 8. And it doesn't use any other information from these 3 when you compress cosmological parameters. So when you compress cosmological parameters, this is what is shown in the left panel. You see that when you do full modeling fit and you compress directly H and small W lambda CDM, there is like a clear disagreement in terms of size of contours. So there is clearly full shape is using more information than what these compressed variables is doing, right? Because otherwise you don't get these different contours. So the way to see where this extra information is coming from is actually put this model in the star, which is well within what the standard compressed variable approach predicts. So it's within 1 sigma, but it's very, very sigmas far away from the full model and fit. And this is what is done in the next slide, is exemplified in red. So you see, when you look at the red, you clearly see what's the difference. I mean, red and blue are both consistent with the same cosmological compressed variable. So both have like a similar BO peak position, and both predicts like a similar amplitude of fluctuations. But therefore, there are some differences that make them to predict different constraints in terms of cosmological variables. And this is what this plot tries to exemplify. And this difference is actually the broadband shape. And this is what it is done in this paper, is to this figure actually is placed to motivate that there is extra information we can extract from the compressed set of variables, just adding on the top of these 3 BO along the line of sight, BO across the line of sight, and amplitude of perturbation, we can add an extra compressed variable which accounts for the shape of the power spectrum. So if we do so, we recover the power of full shape analysis in terms of cosmological variables. This discussion has nothing to do with the fact of the arbitrary choice of our reference templates to produce our compressed measurements of variables. So this is another topic to discuss, but I think there are like 2 different things. One is information content, where this extra information from full shape comes from, and the other is whether your arbitrary choice of reference template affects your systematics in terms of compressed variables. So just to summarize, if we just look at these 3 variables, BO along and across the line of sight, amplitude of perturbations, there is difference in terms of information content with full shape. Where this information comes from, I tell you, is the broadband shape. Essentially, is the tilt of the broadband shape at large scales. If we add this tilt as an extra parameter, then we essentially got almost the same information as full shape analysis. There is a bit of X information we don't recover, but we don't do it because we don't want, but it could include another variable, which is coming, for instance, from the amplitude of BEO in the late time universe. This also contains cosmological information and gives you a bit more information that full shape is able to capture, and current the compressed variables is not, but I mean, it's easy to include just an extra variable that just regulate the amplitude of this BEO.
Okay, thanks. Tillman, do you have anything you want to add at this point?
Nothing specific. Well, generally, I mean, the question is, are things model independent? How much information is there? But I think in the end, we have a specific survey, be that BOSS or DESI or Euclid, and that comes with its own statistical power. And I think it's meaningless to talk about precision without taking the actual statistical power into account. So sure, I mean, at some point, both full shape and template-based things will break down. The question is, does it happen in a regime that we actually care about?
Marco, do you have anything you want to say?
Well, certainly, I cannot say much in a very short amount of time, because I think Hector asked like a lot of. I mean, he raised a lot of important questions. I didn't want to discuss the content of the information content. I just wanted to say that if you do the standard, by standard I don't mean like the latest method that you introduce, but just the standard like F-sigma-8 alpha power particular analysis, you will get the orange contours after the reconstruction, fine. And then I'm just saying that within these contours, you can, if you vary cosmologies and you choose them from random places, you will end up with feeds which look like this, generically like this red line, which are far away from your true data. And you're absolutely right. There is some. This means that there is some additional information that you can then capture maybe in some way. But all that I wanted to say here is that already starting with this analysis and choosing some random template, let's say, and then doing the feed may cause a little bit of a bias. And I also completely agree that this question should be asked within a particular context of a given survey, because they're very much volume dependent. As you shrink the error bars, of course, maybe something which looks fine for a smaller volume may break down for larger volumes. And perhaps maybe here is a good point, if I may just ask for one more slide, which is the last slide, I think. So I understand that Hector has some comments about these results, and perhaps he can bring this up again. But just as an illustration of what I'm trying to say, this paper does the analysis where they basically use the fixed template, which they apply to various cosmologies, but they vary omega matter. And you can see that on the top panel that for extreme values of this choice, if omega matter is too small or too large, they can be even of the order of like a 10% or a few, at least 5% or 6% biased in terms of what the inferred value of F-sigma-8 is. Okay, if you use just the standard analysis, the Hector's method that he introduced recently is maybe more details and perhaps will perform better. But these are kind of issues. Now here, we're talking about F-sigma-8 of order, I don't know, 5 to 10%. So fine, you may say, well, this is good enough for the current data. But when we measure this quantity to like to a few percent precision or 1% precision in the future, this issue will come back. So yes, this is the concern, which I think it's a generic concern, and that every time you introduce a new parameter in the fixed template method, there is always a fear that some model or some volume in the next stage will not work. So my general question is like, how do we deal with this?
So is it maybe a good summary that perhaps everyone would be on board with this summary at this point, that as the data gets more precise, templates that were used in the past might start to be biased or not include enough of the information to match the precision, and therefore need, in some sense, updated in some way to include the information to still be able to get cosmological data giving us parameter constraints in an unbiased way. And then the discussion doesn't necessarily become, are the templates usable? It's just, how does one have to improve them? And Hector's paper that we're looking at figures from, or this one perhaps not, but the previous ones, is a process of doing that. Is that something that everyone would agree is a correct statement?
I mean, it depends on what model means, right? Because then there is this problem of you observe galaxies, you don't observe dark matter, and then galaxy formation is a very complex process. You have history formation in terms of halos, which gives you assembly bias, and even within, if you assume that there is no assembly bias, there is kind of processes within galaxies that make them perhaps have non-local relations in terms of bias, and this gives you a very wide complexity model that in terms of galaxy bias that you have to account. And if you don't do this right, this can bias your physical parameters or your cosmological parameters. So in that sense, yes, there is a limitation coming from theory, but this is not exclusively coming from dark matter perturbation theory. It's just galaxy formation as well, which is way more complex to address analytically.
Okay, but then as one is, so say for example, taking F sigma 8, as one is getting more precise, this F sigma 8 can't be the full description anymore, and you do need to introduce extra parameters to account for this extra physics that is now being kind of measured in some way. Is that still a correct statement? Because I know that in this pre-discussion you were sharing kind of rescalings of the parameter, that you had to introduce a new parameter. Is it now a good time to sort of talk about that methodology?
Yes, I think so. So let me say, I think you were mixing some concepts, because
Sure, cool, thanks. Please correct.
when you extract information from velocities, you extracted, I mean, there is just one single parameter within GR, which is scale independent, which is the growth of a structure. And that in principle describes the full thing. The problem is that these parameters entered in very complex way into your P of K shape. And for instance, at small scales, you have that these parameters regulate the fingers of God amplitude. But then I think you don't want to extract information by measuring fingers of God, because this is super model dependent. And then your assumption, so your output, it's going to...
Sorry to be annoying again, but just for the audience who may not be familiar, can you just quickly talk about fingers of God and what it is?
There are essentially two regimes in what peculiar velocities are, which is just the linear regime, which is essentially what a Kaiser model predicts, which is just linear infall on galaxies towards themselves. And this is where most of the information comes when you measure RSD type of analysis or F sigma 8. But you can go to smaller scales, and then you go into intra-halo, and then you observe how the dispersion of velocities inside the halo behave. And this distribution depends, among other stuff, depends as well on F, the growth of the structure. So the stronger the gravity is, or the more matter you have, then you have higher dispersion, right? So by measuring how high is this dispersion, then in principle you can infer cosmological parameters. The problem, I mean, if you do this on the linear regimes, it's kind of easy because everything is linear and you more or less know the theory. But if you go to very small scales, then there you have to put very tight constraints on your model to describe these things. So I don't think you want to do cosmology based on that. I mean, if you want to do this, then you have to be aware that this is going to be very model dependent. So your prior in the model you put, it's going to affect a lot on your output. But this is just one question. The other question that we were trying to address is the impact of your reference model when you do compressed variable fit, right? And this is what Marco was showing in this last plot. That it was showing that when you were choosing simulations far away from the model, and you were measuring this F sigma 8, and you were getting this systematic offset that it seems to depend with the value of omega matter, right? But this is coming from a paper where, in my opinion, they haven't been properly addressed what F sigma 8 means. And the issue is that the definition of sigma 8, it's very subtle, because you defined, as I've said, F sigma 8 is the amplitude of fluctuations of the power spectrum in spheres of 8 megaparsecs over h. But then 8 megaparsecs over h, which is the h? This h is the h of your template. Therefore, if you choose templates with different Fs, with different Hs, then you are going to smooth your power spectrum in spheres of slightly different size. And this is going to create a conflict in what the actual physical definition of what you are doing. So actually you have to correct for that when you actually have used a template that end up being a bit far away from what your data cosmology want. So you have to rescale all these into just to be the same parameter, which is F sigma 8, but this 8 expressed in megaparsecs over h of the universe instead of h of the template. If you do this, if you rescale this by this factor, then this dependence that Marco has shown in that plot, it goes away. So it's just a question of properly defining your variables.
Right. Marco or Tillman, do you have thoughts on that? Because it seems like quite a crucial point that maybe, I mean, certainly me as an outsider, if I see a paper say F sigma 8, I would not be particularly likely to recognize that. But
well, me neither. I think that this discussion exactly shows that this fixed template analysis is not so simple, I think, at the end of the day. I mean, yes, maybe you can do some additional tricks, you can introduce new parameters. At each next level of precision, we have to introduce more parameters. So it is not clear to me how does this converge? Like, how do we know in a systematic way that we are always going to be fine, and what are exactly the rules of the game? And this shows, I mean, this kind of discussion exactly shows these difficulties. Now, yeah, I don't know what to say about the rescaling of I'm not sure if age was really varied in these simulation boxes that they have. I don't remember this. I do know that in some examples that we checked for some kind of combination of DESI or Euclid and Planck, we did some examples where we don't change age. So our age fiducial is the correct age. So I don't think this problem is there. But we did still find in some Fisher forecasts or some real MCNC chains, some with the mock data vectors, we did find that there are biases still remaining when we use fixed template analysis with the wrong assumptions. Not so far from true cosmology, but with the wrong assumptions about omega matter, for instance.
But I'm not sure which specific cases you're referring to, because I mean, in my opinion, if you do things right and you compare apples with apples, which is what you should do, it doesn't matter whether it's difficult or not, you should compare always apples with apples. If you do this, then you don't get any strong biases in choosing arbitrary templates. And I mean, I can exemplify this. I mean, if you look at figure at the slide 8, so there you have, I mean, I'm not showing the effect of the broadband, but I'm showing a series of templates where they look quite different, right? These different lines in the right panel, in the left, sorry, yes, in the left panel, sorry, the oscillatory features are really very different, right? Also, the amplitude of the BEO is pretty different. Then you can go now on slide number 6. So you have these different cosmologies on the x-axis, and we are fitting signal, where the true template is what it says Pachi. So if you look at the green lines of Pachi, that's what you get when you use the true template from the simulation, so what the template wants. Of course, you observe like a bit scatter as you go within the horizontal line, but then there is no hard trend I'm seeing when I'm moving from template to template, that these templates are very, very different. They are very far away from one plant once. And I don't see any trend that, I mean, I see there's some oscillations, obviously, but I mean, yeah, that's very, very small variation. So for reference, this is divided by a statistical sigma corresponding to 3 gigaparsecs cube volume. This was the volume of one of the samples of Bose. Obviously, DESI will do better than that. But you see that, I mean, within these templates, and these are like very, very different templates and very far away from Planck, I mean, there's no strong dependence. It fluctuates a bit, but I mean, yeah. So I think maybe what you were doing in this other plot is just that they were not comparing proper parameters with, I mean, you were not comparing variant parameters across templates. And I agree that you have to be careful with this. You always have to work in parameters which don't depend on the templates you choose. But I mean, this is not that difficult to do.
Tillman, you haven't had too much input on this particular topic. Maybe as a kind of neutral-ish bystander, you can share some thoughts about Hector and Marco's perspectives. I mean, I don't think it's so much that Hector and Marco are disagreeing on whether it's possible. Maybe just Marco has some reservations that you have to be very, very careful to make sure that your templates are staying precise, and Hector is more confident that is possible. But what are your thoughts, Tillman?
Yeah, I really think it's a question of scale. I mean, if the plot that's on figure on slide 6 that you just looked at, if that's a current survey, then I would be concerned about having biases of half a sigma. It's really just a question, where do you draw that gray band that you say that's okay because things break down under that level anyways. Also, yeah, sigma 8 is a horrible parameter. There's so much stuff going on there, and trying to parameterize stuff in sigma 8, it's causing pains all over. But I assume Hector would also agree that if you were to choose some template that's 10 sigma away from the truth, you're probably running into problems. If you're happening to get the right thing, then it's fine. So it's really just when does your perturbation around the truth run into issues when you get too far away from the real model. And I think that's just an intrinsically survey-specific question that should be asked beforehand, and then you set what is the precision that you need, and then you do your survey until in a blind way, so you don't try to explain post hoc on what's okay to do.
I mean, you can always iterate on the reference template. So you can start an arbitrary template, do your first analysis, and then based on the cosmology you get back, then you can reanalyze based on a new template and iterate a few times, and then you are essentially there. So if you're worried about, well, if I don't have CMB, then starting from an arbitrary point will give me a very bad chi-square, fine. Then in that case, you iterate a bit until you get convergence, and that's where you will be hitting the same where Planck is, more or less.
But this iteration is really doing then the full shape by hand, rather than exploring like all possible cosmologies in MCMC. You're doing it yourself, and just you're going towards the local minimum.
You do a full MCMC, and then your results return you some alphas, right? That they are different than 1 because you have used a wrong template. Then based on this different than 1, then you can figure out which is the template that makes them to be 1. And then you start reanalyzing again. And then in this new analysis, then your alphas will be close to 1, and that's the end of the story.
So the last question is, when data isn't independent, so when you have more than one survey, and it seems like from the pre-discussion at the moment, thankfully, this isn't actually a big issue, that the spectroscopic surveys and photometric surveys seem to be in different hemispheres and stuff. So when you're combining data, they're actually roughly independent. But in the future, that won't be the case. How do you combine the data? You can't just multiply likelihoods. And the vibe I got was that for full shape analysis, you kind of have the full covariance of all the parameters as part of the model. So it might be like difficult for your computer to process everything, but in principle, you know what it has to do in order to calculate the full combined likelihood. But in the templates, maybe it's less obvious. So Tillman, do you want to start by maybe explaining what I just said more correctly and perhaps more depth? And then we can talk about how one might achieve that.
Yeah, I think there are 2 points to consider. One is just having a large-scale galaxy survey by itself and some other probes that happens to be correlated in some way. And then you can say just, well, we need to account for that because those are not independent, either because there's a sky overlap and or redshift overlap, and then you need to account for the cross covariance. The other part is saying that knowing that you have correlate data sets, can we get X information out of the cross correlation between them, which is a whole different issue. In this case, let's say we have a big lensing survey, and we could do like galaxy lensing, so cross correlation between the lens galaxies from the spectroscopic survey and the background source galaxies. And because it only has basically a factor of the bias only comes in once compared to that is squared for the galaxy clustering, that would help break some of the astrophysical stuff that you might have trouble with just pure physical perturbation theory. So in principle, that would be something interesting to do. And if you want to do something like that, then you need consistent modeling for all your different probes, in which case it's probably easier from using a full shape analysis for everything, because most other cosmological probes don't or can't use template-based methods. So you would have a single modeling framework to do everything. But on top of that, then you need to deal with the covariance and cross covariance between these parts, which is very complicated thing even for the single probes. So there I wouldn't make any statements on which approach would be better. Just because I think that's a open questions in any case.
Awesome, thanks. So Hector, maybe do you want to go first in responding? Because it seemed like you agreed here that there's work to be done. So what work has been done and what work needs to be done? And then, of course, once Hector's finished, Marco, you can try.
Yeah, I mean, I don't have much experience on this cross-correlation topic, especially with weak lensing, but I think that within clustering, you can always make a connection between the covariance of P of K and the covariance of the compressed set of parameters. Just having enough mocks, you can do this. So for each mock, you measure the set of best fit parameters, and then you can cross-correlate the covariance between P of K and the covariance between compressed parameters. So if you have this bridge between these two, then you're done, because I mean, then the other difficult part is to establish the bridge between the P of K and the lensing part, right? But then you have this bridge, and then with this other bridge, then you can build a full covariance between whatever observable you have in weak lensing and the observables you have in clustering. So I don't see this as much of a problem or an extra problem with respect to what full modeling will have.
Any further thoughts, Tillman, on Hector's thoughts?
Yeah, I mean, yeah, in general, I mean, I think it's all possible. I think we can agree on that. It's just how much effort to be put into. The problem with using mocks for weak lensing is that weak lensing just has annoyingly high requirements for mass and scale resolution to convert, at least for the scales that are currently being used. And that's why currently everything is converging analytic approaches, which I think is also doable for the clustering part. And I think there's been work on that. It's just, I think no one has actually sat down and implemented that in an easy to use manner.
But I was saying that you have analytical covariance to link the P of K in clustering with the P of K in lensing. Then if you have mocks just for clustering, not for lensing, but just for clustering, you can use these mocks to actually bridge the P of K in clustering with the variables observed in clustering. So with this bridge and the theoretical bridge you have between P of K's in clustering and P of K's or shear in lensing, then you can build up your full covariance. This is what I was saying.
Yes, I think that might be approached. The question is if the P of K from the mocks goes sufficiently scales that it can be mapped to the P of K we need for the lensing. But yes, in principle, I think that would be an approach.
Any thoughts on the topic, Marco? Maybe, well, I mean, feel free to have independent thoughts to the one I'm about to suggest, but perhaps along the lines of the full shape analysis and how one might.
Yes, I don't think that. Well, traditionally, maybe if you want to be very conservative, you can just produce a large data vector which contains both lensing and clustering, and just calculate this covariance from the mocks. Now, of course, this is very difficult because the data vector is very large. And I think that in that example, for example, using some sort of compression, I don't think this is a problem. You can, for example, reduce the number of variables or data points, and you can then calculate covariances for this. I also think that analytical covariances are good enough, at least for current generation surveys. We know that this is true for clustering, so we don't even need mocks to do, for example, Gauss analysis. We will find exactly the same contours if you just use a Gaussian covariance, basically. Now, for the lensing, I don't really know. I have never studied this myself, but I think that we can make a lot of progress just using analytical covariance. So I don't think that there is really let me just maybe summarize. I don't think there is a fundamental problem in using compressed variables to combine with the lensing. However, I think that maybe what was raised as one of the interesting points is that if you compress something, you lose all the information about bias parameters, which maybe in combination with the lensing will gain a lot of information about biases, which in turn can lead to some improved cosmological parameters. So again, it is the same story about as before, like whether this compression is optimal, whether do you capture all the information that there is, or you just throw away some information. In the full shape, again, you're guaranteed that you will get everything. So maybe, and from that point of view, it is maybe more straightforward and simpler to implement. But I don't think that if you do a proper compression, which you don't throw away anything, I think that then you probably can also build a covariance for these compressed variables.
Any further thoughts, Hector or Tillman? If someone in the audience is lacking a research project and wanted to dive into this particular topic and help do something that will make the combining of data more feasible, what would be something that they could sort of start diving into? Or is it something that needs quite a large collaboration?
No, I think covariances are just always a pain. For anyone who has worked on them will know. What I would be interested in, could you make a template-based method for lensing that works reasonably well?
I had a very similar question I was going to ask eventually, which is a template method for the CMB. And the reason why I thought that might be interesting is that there is things like this H0 tension, and there are other sort of things that may or may not be suspicious in the CMB. So I was very curious about whether one could kind of take the philosophy that Hector has pointed out, which I think sounds quite compelling to me, of taking your full data set and isolating what each separate physical process is telling you about the universe, and then extract it. So I guess Licia Verde has said in the chat that the Kasowski parameters is one thing. Yeah, is there like an algorithmic way to construct new ones that one could do in the CMB? And does someone want to say what the Kasowski parameters are? Because I have no idea.
Well, me neither, but I think that some attempts along these lines have been done to somehow decouple, for example, the late universe from what is really in a model independent way measured from the CMB. Because of course, when you make a CMB predictions, you have to know the distance of the CMB, you have to assume some dispersion history. So in a sense, if you marginalize over all these things, you may want to really isolate what CMB truly tells you. And that would be things along the lines of the ratios, the heights of acoustic peaks, things like that. So this would be some equivalent of like these alpha parameters or F sigma 8 and things like that. But I think that in the CMB community, there is a reason why people did not pursue this. And it was exactly all the reasons that I mentioned at the beginning, that while this might be an interesting exercise to do, like if you're really not sure what is happening with your data and you really have doubts about maybe some systematics and you want to decouple late universe from the early universe, that's fine. But if you really want to gain all the constraining power from the CMB that you can, I think that it turned out that the full shape analysis of the CMB was the way forward. And this is what
I think the reason why it was not used in the CMB was that so in the large scale structure, there are like late time variables and early time variables. So you have the shape of the power spectrum, which is essentially coming from transfer function, which is early universe. And you have BEO, which you have a bit of a mixture, but essentially is late universe. And then you have F sigma 8, which is super late universe and perturbation level. And in CMB, you have just one snapshot very far away from time when things happen, and then this get imprinted there, and then it travels through us in time with some effects.
But these are important effects, like CMB lensing is very important. And it's
yes, exactly. But
it is an important late universe parameter. And then also the distance to the CMB knows about the entire expansion history. So also it is an important.
I think it's mixed there. I think it's so naturally decoupled. So when you work if you want to parameterize this in compressed variables to the CMB, it doesn't naturally decouple in early and late times. And I think that's something that this is why for the CMB is not such interesting to do so, but for the large scale structure it is.
Just Licia is writing some interesting stuff in the chat. Just a quick question. Licia, are you willing to just sort of turn the mic on and share some thoughts? Or if not, that's totally okay. Obviously you arrived as an attendee, not as a panelist, so you don't have to feel obliged. Just if you feel keen, that would be cool.
Sorry, it's just that I have kids around, so I may mute every now and then if they start fighting. So for the CMB, the physical parameter exists, right? They were introduced when doing a full MCMC were still computationally expensive, and therefore you needed to find a way to do that faster. And that was a big speed up. And some of these parameters are still being used, right? The theta parameter that they still use now, it's with the position of the peak, is derived from that. And for a while they were used, this compress constraint from the CMB that get published every so often, and then people outside the CMB community use because they are model independent. Those are still being used, but of course they are not as powerful as doing the full fit, but mostly because the CMB is only a one redshift, right? So you can't disentangle as you can do with BAO, where you have the relative information at different redshift. And so all the late time universe sort of gets in the way. There is a way to get rid of the late time universe information. And I was trying to look for the reference there. Now I forgot who was the first author, but I can find it out. You can marginalize over lengthing, well, not marginalize, but you sort of get lengthing out in an effective way. And then you can get the late time physics out in an effective way through the position of the peak. The only thing that is very difficult to handle in an effective way is the ISW, right? So so at least nobody has found a way to actually get the ISW out in an effective way as if they were compressed variable. But
okay, is this what you were referring to by the Kosovsky parameters, or is it?
So the Kosovsky parameter are the physical parameters. So where they say the ratio of the first and the second peaks tells you about the ratio between omega matter and omega baryon, and then the ratio between odd and even peaks, and then the position of the peaks tells you about the late time, compounded with what you know about the sound horizon. So all these things, they're written in that paper, and they are derived that way. But for the CMB at the end, you need to run a Boltzmann code if you want all the details.
Yeah, well, so this is the thing that maybe is one of the key issues that I think maybe Marco and Tillman were getting at in the model independence thing, that maybe at the moment you don't need to for the large scale structure, but at some point things get muddled enough, the different physical effects, that and it seems like in weak lensing this is already the case, and in the CMB it's certainly already the case. So yeah, maybe a question at Hector. What are your thoughts on that? Is it possible that eventually we get to a level of precision where the effects from various different physical processes are just muddling together too much that it becomes like weak lensing in the CMB? Do you foresee that, or is that missing the point somehow?
You mean in the large scale structure analysis?
Yeah, and for spectroscopic surveys.
I think it comes to very small scales, right?
But not even at large scales once they're precise enough. The same way that the integrated Sachs-Wolf effect is just this nuisance that is there, and you just can't get rid of it.
I haven't done the math, so I really cannot say. To which, I mean, I don't know. that's a quick question. That's a quick answer. Fair enough.
Okay.
If I may just add, I do believe that the next generation surveys will be a transition to this regime where, similar to the CMB, we will have to transition to the full shape analysis, also into large scale structure. And one important thing that Richa mentioned, maybe very briefly, is that, of course, people used to do this simple parameterization at the beginning where the analysis was expensive because it would take forever to run MCMC. And something similar was happening also in the large scale structure. Nowadays, we have technologies to do the full shape analysis very fast. And I think that this is also one important point which will trigger this transition, in my belief.
Okay, this might be a natural time to kind of start concluding. Let's go through the panelists individually. You can just sort of summarize what you have. Let's say the framing question can be how you've changed your mind based on the pre-discussion and this panel event discussion now, and in which ways you think you've gained some important insights. And we'll go in reverse alphabetical order this time. So maybe starting with Tillman, ending with Hector.
Yeah, so I think I really have come to appreciate how you can do this template-based and physical parameterization of large scale structure. So if I were to sit down and had to do one, I would go with that. I think you have convinced me that at least the current surveys that's good enough. And yeah, I wish we could do something like that in weak lensing where we can just factorize out different parts that goes into our final constraints. Because a final question would be, if you convince yourself that everything is fine with your template-based methods, that everything behaves as you would expect, would you then, what steps would need to be done to then go on to do the most constraining analysis with some full shape or beyond that. So I completely agree. To use templates-based methods and physical parameterization to understand the data, that's a great tool.
Based on the conversation.
Well, I don't know if I changed my mind about many things, because I already had a lot of these kind of discussions with various people since this full shape analysis came online. I think that, let me say, I do understand, and I do understand that sometimes to be very cautious and try to go slowly with the new data set, you may want to do some analysis which is more, where you have some physical intuition about what you're supposed to get, and you can do some cross checks. But I think for the next generation surveys, once we are sure that things are okay, I think the optimal way to analyze them will be similar to what happened to the CMP, to use the full shape analysis. This will give us the best possible constraints on cosmological parameters and the highest probability to find that something is maybe inconsistent or break lambda CDM, as Hector is saying. Yes, I think that I'm still very much worried about the model independence and high precision level of the fixed template analysis. I do understand, as Hector showed, that you can improve the standard analysis. And then I think that there is a lot of work to be done, I think on the side of the people who want to use it, to explain at which stage it breaks down, if like what happens, for example, when you add neutrino masses, because now you cannot mimic neutrino masses with omega matter, you need another parameter, and so on and so forth. So these are all, I think, open questions for the future. And the good thing about this is that I don't think that they even need simulations. All these things can be answered on the level of some Fisher forecast or some little bit more complicated analysis. So okay, I do believe that we can relatively quickly answer these questions and try different options.
Well, I mean, I haven't changed my mind a lot, I have to say. I mean, I have like similar concerns that I've said at the beginning, which is like, there are situations where full modeling approach is probably the right way to go. And these are like essentially when two conditions are held. One condition is that there are no systematics in the data. The second condition is that we know for sure that this is the right model of the universe. But if we move away from any of these two conditions, I don't see that the full modeling approach is like the most practical way to go, because what we want to end up doing is robust analysis. And this is actually checking that everything is okay with the data. So in order to do this, I think doing the compressed variable analysis has its value. And on the other hand, also we want to check whether a model is correct or not. And again, doing compressed variables is a way to go into this sense. So, I mean, I would summarize it in this way.
Hello, post-panel event, me again. Somehow I completely forgot to thank the panelists during the event, so let me take this moment now to say thank you, Hector, thank you, Marco, and thank you, Tillman, for your great insights, and thanks, Lucia, for jumping in during the event to share your insights. And that's the end of the video. If you're feeling generous, don't forget to like and subscribe.